All right, I'm talking about compliance assessment or conformity assessment using the phrases pretty much interchangeably for the moment. So thesis, I suppose, is that we do an awful lot of measurements to check compliance with something, a specification or a regulation. We've spent a lot of work in the last 20 odd years trying to get measurement uncertainties for chemical measurements. And we now have to take those into account when we're using our measurement results. And so the questions that we would like answered are, how do we do this? And a secondary question, particularly now that ILAC G8 has been published, how does it help to control risk? So I'm going to talk a little bit about all of those points, a little bit about basic use of results in limits, and a little bit about how measurement uncertainty can help us to quantify risk and to understand it, and how rules can help us control those risks. So we start with a familiar picture. We have a series of results. Let's say here we have an upper control limit. This result is above our control limit. Pretty unambiguously, we would regard that as not complying with the limit. Similarly here, where we're close to the limit, the results above, if we just look at the results, we conclude these don't comply. And similarly, at the other end of the scale, we can see that we have results below the limit, which clearly do comply. There's always one case right in the middle here where it's not so clear what to do with this. And this is the first case that we meet, even without measurement uncertainty, where we need some additional information. We need some rule or basis for handling this borderline case. It might be rare if we're looking at individual results, but it still happens occasionally. Once we've got uncertainty in the picture, of course, things change a little bit. We're probably still happy with this picture where we've got an expanded uncertainty here. So we're pretty sure that the true value is somewhere between these limits. And that means that we're pretty sure that our test material does not comply with this upper control limit. It's above the limit. And at the other end of the scale, again, we've got an uncertainty interval that's wholly below the limit. We're comfortable that that complies. But we've now got three cases in the middle where it's not so clear. Do we take that as complying because there isn't really strong evidence that it's above the limit? Do we take this as complying, or this? And for those, we clearly need even more rules. So it doesn't take us long to work out that if we want consistent decisions in these circumstances, we're going to need some rules. Now, our guide on this topic starts with some guidance that was produced by ASME, which is an American standards group. And it asks essentially for three things. First, it asks for your specification, your product specification or your legal specification that tells you what you're allowed. And that's usually in terms of the amount of substance in your test material. You then need a rule to tell you how the uncertainty will be taken into account. And for some of those rules, you can form what's called an acceptance or rejection zone, which is a range of results which you'll take as indicating an acceptable test material. And these rules, decision rules, have a definition nowadays. It's just a rule that tells you how to use the uncertainty. ISO 17025-2017 added this. It also said, for the first time, if a customer asks for a statement of conformity, you must have a clearly defined decision rule. And that was a new addition 5 years ago. then it was only if the customer requested an uncertainty, you should give it to them for testing. But nowadays, if your customer is asking you to tell them whether your test material complies or not, you must have a defined decision rule. What do decision rules look like? I suppose is a good question. Here's an example. That's the rule in English. It says a result equal to or above the upper limit is non-compliant. And the converse of that is that the result below the limit implies compliance. Now, there's a picture of this over on the right. Let's say we have a limit for a product or a legal limit for something. This rule says any result up to here complies, is a compliant sample. Any result above here is a rejection or a non-compliance. Now, I mentioned acceptance zones. That rule says that any measurement result from the left up to our limit is acceptable. So that's called an acceptance zone. It happens to be the same as what ASME calls a specification zone in this particular case. When they're the same, there's a name for that. It's called simple acceptance. And it's called simple acceptance because it says, just look at the measurement result, the value, the reported value. Don't bother with the measurement uncertainty. That's sometimes also called a shared risk approach. And that's because when we're close to the limit, essentially when we're at the limit, there's a sort of 50-50 probability that the test sample complies or does not comply. And that means that the person who's producing the material takes some of the risk and the person who's buying the material or the item takes some of the risk. I will say that for this particular decision rule, it's usually important to have an upper limit for the measurement uncertainty, because if you don't, you'll be running quite large risks. And we can see why here. If we take our picture of an upper limit, so our test material can contain as much as this, but no more. Let's say we have a measurement result just here, just above the upper limit. Now, we all know that that isn't an exact value. We all know that there's an uncertainty on that. So if we put the uncertainty on some kind of a distribution, you can see that there's quite a lot of this distribution that's below the upper limit. Now, the usual interpretation of a measurement uncertainty distribution is that this is the range of values that we might actually believe is in the test material. So the test, we've got an observed value of, let's say, 10.2. Anything between, let's say, 9 and 11 is reasonable for the actual amount in the material. And obviously our upper limit would be perhaps at 10. The important part of that is that this limit, you can see that if this is a distribution of possible true values, let's call it, quite a lot of this distribution is below the upper limit. In other words, there's quite a large probability that the test item actually complies. So we're not that sure that the test item fails, even though the measurement result is just above the upper limit. So what we have there, this green area, we can call that a compliance probability. Based on our result, we can say that's the estimated probability that our test material actually complies. And of course, this yellow region is the probability that it doesn't comply. Now, if we want to keep those risks of false declaration, because this could well be a false declaration either way, we'll probably say that this doesn't comply, but at the moment it looks like there's a good chance that it might. So this is if you like, the risk of a false declaration of non-compliance. If we want to control that risk, if we want to make that small, the simplest way of doing it is to keep the uncertainty small. Usually, in these circumstances, with simple acceptance, a small uncertainty means that the risks of false declarations are small. The other way of looking at it is that if we want small risks of false declarations, we need a small uncertainty, which is why those arrows go both ways. We can see that in a picture. If we have the same situation, but a much smaller uncertainty, you can see that this compliance probability is much smaller. It's a much smaller proportion of the overall probability. So if we're using a rule like simple acceptance, where we just use the measurement result to decide whether something complies or not, small risks need small uncertainties. Now, we can't always have a small uncertainty, unfortunately. There's usually some, there's always some, sometimes it's big. And that's particularly true in things like chemistry at low levels, where very often the limits are close to the detection capabilities of our test methods. But we can use different decision rules. This is a simple decision rule, but there are other decision rules. So we can use decision rules to control the probabilities of false decisions. We can't control them all, but we can control at least one of them. And the way that works is to go back to our picture. We say, well, if we had an observed value down here with an uncertainty just the same as before, we've got a compliance probability here of about 95%. So that means that we've got a false declaration probability of only 5%, and that's quite reasonable. So let's say that we wanted to make sure that our false rejection probability is always 5% or less. What can we do? What we can do is we can change our rule. We can say, instead of using the upper limit as a criterion, let's use this value as a criterion. Let's put some gap between the specification, the edge of the specification, and the edge of the acceptance range. So we're now defining a smaller acceptance range, and that gap, this grey thing here, is called a guard band. And that's a standard way of controlling risks of false declaration. In this particular case, this controls the risk of a false declaration to 5%. Now, there are two extreme ways we can set up guard bands. We can set up a guard band that is outside the upper limit, outside our limits, so that our acceptance zone, the region where we believe a measurement result can be marked as compliant, is a little bit bigger than our product specification or our legal acceptability zone. And that's something that we might do when we need quite strong evidence to reject something. And there's a name for that. It's called relaxed acceptance, because we're quite happy to accept material that runs quite a high risk of being out of compliance. The other rule is called stringent acceptance. And that means that we are, if we have a result inside this acceptance zone, we are very sure that the result, that the test material does in fact comply. And that is actually the default in ILAC G8. It recommends that if you haven't got a rule, you use this kind of rule, which says basically take the expanded uncertainty away from the limit before you apply your decision. So make sure that your whole uncertainty interval is inside the limits. And we can see that those have different effects on the probability of acceptance and rejection. As I said, stringent acceptance, this green picture here is ILAC G8's recommendation if in doubt. These can be two-sided. So this is a stringent acceptance set up for a two-sided specification. And all it means is that we've got an upper and a lower limit, and we need our measurement result to be inside this region here. And that guard band is set using the measurement uncertainty. So that's usually set to approximately the expanded uncertainty. And that's the basis of the Eurachem guide. It requires decision rules, and it uses the concept of guard bands to set an acceptance zone so that we can look at our measurement result and we can say, is it within the acceptance zone? If the result is in the acceptance zone, we pass the sample. The advantage of that is that you've now got a clear method of determining where a result should be marked as compliant. And we can also control the probability that the, if you like, the true value for the test material is within the permitted specification. The other thing that you might want to worry about, and I'm not going to spend time talking about it now, is that we do still have to worry about whether we're doing a single measurement or an average of several measurements. And we do have to worry about the possibility of outliers. And usually that involves a retest if we get an unexpected non-compliance, just to make sure that we're correct about it. Or it may involve a retest if, for example, we're within the expanded uncertainty of the limit. Our guidance document does deal with some other technical problems. I'm just going to list those. The first one is that everything I've said so far assumes that the uncertainty is in the units of the measurement result. That is, it's an absolute uncertainty. But sometimes the uncertainty is given as a percentage and it's proportional to the level. That can affect the guard band. There's a very simple rule there, and that's that if you have a relative uncertainty, the guard band is set as if the result was at the legal limit and not around a measurement result. There's a reason for that, which is explained in the guide. Another issue is that we do see some cases, particularly with large uncertainties, where the uncertainty interval can be asymmetric, it can be bigger on one side than the other. That is dealt with to an extent in the guide, and some suggestions are given for handling that. It's also possible to write decision rules that give you a pass, a fail, and an inconclusive answer. That's also in the guide. And another thing that is slightly intricate is setting this size of the guard band. It's usually set as the expanded uncertainty, but if you want exact 5% probabilities of false declaration, then you actually need to use a one-sided value of students t. In other words, instead of using k equals 2, the guard band would be set with k as approximately 1.65, which is slightly smaller. That means that if you're using k equals 2, you're doing a little bit more than you have to protect your usually customer. Wrapping up, if you want to state whether a test material complies with a specification, you obviously need a measurement result. You also need an uncertainty that goes with that result. You need a specification for the product or for the legal limits. And perhaps the most important thing is that you need to specify a decision rule. And increasingly now, you will need to refer to a decision rule if you're reporting on compliance, if you intend to comply with ISO 17025. That's all I'm going to say today. There is more information in the guide, which is free on our website at eurachem.org. So thank you very much for your time and attention.